An aurora, sometimes referred to as a polar light, is a natural light display in the sky, predominantly seen in the high-latitude regions. Auroras are produced when the magnetosphere is sufficiently disturbed by the solar wind that the trajectories of charged particles in both solar, wind and magnetospheric plasma, mainly in the form of electrons and protons, precipitate them into the upper atmosphere, where their energy is lost. The resulting ionization and excitation of atmospheric constituents emits light of varying color and complexity. The form of the aurora, occurring within bands around both polar regions, is also dependent on the amount of acceleration imparted to the precipitating particles. Precipitating protons generally produce optical emissions as incident hydrogen atoms after gaining electrons from the atmosphere. Proton auroras are usually observed at lower latitudes. Different aspects of an aurora are elaborated in various sections below. Occurrence of terrestrial auroras. Most auroras occur in a band known as the auroral zone, which is typically 3 degrees to 6 degrees wide in latitude and between 10 degrees and 20 degrees from the geomagnetic poles at all local times, most clearly seen at night against a dark sky. A region that currently displays an aurora is called the auroral oval. A band is placed towards the night side of the Earth. Day-to-day positions of the auroral ovals are posted on the Internet. A geomagnetic storm causes the auroral ovals to expand and bring the aurora to lower latitudes. Early evidence for a geomagnetic connection comes from the statistics of auroral observations. Elias Loomis, and later Hermann Fritz and S. Tromholt in more detail, established that the aurora appeared mainly in the auroral zone, a ring-shaped region with a radius of approximately 2,500 kilometers around the Earth's magnetic pole. It was hardly ever seen near the geographic pole, which is about 2,000 kilometers away from the magnetic pole. The instantaneous distribution of auroras is slightly different, being centered about 3 to 5 degrees nightward of the magnetic pole, so that auroral arcs reach furthest toward the equator when the magnetic pole in question is in between the observer and the Sun. The aurora can be seen best at this time, which is called magnetic midnight, in northern latitudes. The effect is known as the aurora borealis, named after the Roman goddess of dawn, Aurora, and the Greek name for the north wind, Boreas, by Galileo in 1619. Auroras seen within the auroral oval may be directly overhead, but from farther away they illuminate the poleward horizon as a greenish glow or sometimes a faint red, as if the sun were rising from an unusual direction. Its southern counterpart, the aurora australis, has features that are almost identical to the aurora borealis and changes simultaneously with changes in the northern auroral zone. It is visible from high southern latitudes in Antarctica, Chile, Argentina, New Zealand, and Australia. Auroras also occur on other planets. Similar to the Earth's aurora, they are also visible close to the planet's magnetic poles. Auroras also occur poleward of the auroral zone as either diffuse patches or arcs, which can be subvisual. Auroras are occasionally seen in latitudes below the auroral zone, when a geomagnetic storm temporarily enlarges the auroral oval. Large geomagnetic storms are most common during the peak of the 11-year sunspot cycle. During the 3 years after the peak, an aurora may appear overhead as a corona of rays radiating from a distant and apparent central location, which results from perspective. An electron spirals about a field line at an angle that is determined by its velocity vectors, parallel and perpendicular, respectively, to the local geomagnetic field vector B. This angle is known as the pitch angle of the particle. The distance or radius of the electron from the field line at any time is known as its Lama radius. The pitch angle increases as the electron travels to a region of greater field strength nearer to the atmosphere. Thus it is possible for some particles to return, or mirror, if the angle becomes 90 degrees before entering the atmosphere to collide with the denser molecules there. Other particles that do not mirror enter the atmosphere and contribute to the auroral display over a range of altitudes. Other types of auroras have been observed from space, e.g., poleward arcs stretching sunward across the polar cap, the related Theta aurora, and dayside arcs near noon. These are relatively infrequent and poorly understood. There are other interesting effects such as flickering aurora, black aurora, and subvisual red arcs. In addition to all these, a weak glow observed around the two polar cusps, the field lines separating the ones that close through the Earth from those that are swept into the tail and close remotely. Images. The altitudes where auroral emissions occur were revealed by Carl Stormer and his colleagues, who used cameras to triangulate more than 12,000 auroras. They discovered that most of the light is produced between 90 and 150 kilometers above the ground, while extending at times to more than 1,000 kilometers. Images of auroras are significantly more common today than in the past due to the increase in use of digital cameras that have high enough sensitivities. Film in digital exposure to auroral displays is fraught with difficulties, due to the different color spectrum present, and the temporal changes occurring during the exposure. The results are somewhat unpredictable. Different layers of the film emulsion respond differently to lower light levels, and choice of film can be very important. Longer exposures superimpose rapidly changing features, and often blanket the dynamic attribute of a display. Higher sensitivity creates issues with graininess. David Mallon pioneered multiple exposure using multiple filters for astronomical photography, recombining the images in the laboratory to recreate the visual display more accurately. For scientific research, proxies are often used, such as ultraviolet and color correction, to simulate the appearance to humans. Predictive techniques are also used to indicate the extent of the display, a highly useful tool for aurora hunters. Terrestrial features often find the way into aurora images, making them more accessible and more likely to be published by major websites. It is possible to take excellent images with standard film in a single lens reflex camera with full aperture, a fast lens, and exposures between 10 and 30 seconds, depending on the aurora's brightness. Early work on the imaging of the auroras was done in 1949 by the University of Saskatchewan using the -270 Seychelles rupees radar. Visual forms and colors. The aurora frequently appears either as a diffuse glow or as curtains that extend approximately in the east-west direction. At some times they form quiet arcs, at others they evolve and change constantly. The most distinctive and brightest are the curtain-like auroral arcs. Each curtain consists of many parallel rays, each lined up with the local direction of the magnetic field, consistent with auroras being shaped by Earth's magnetic field. In situ particle measurements confirm that auroral electrons are guided by the geomagnetic field and spiral around them while moving toward Earth. The similarity of an auroral display to curtains is often enhanced by folds within the arcs. Arcs can fragment or break up into separate, at times rapidly changing, often rayed features that may fill the whole sky. These are the discrete auroras, which are at times bright enough to read a newspaper by at night, and can display rapid sub-second variations in intensity. The diffuse aurora, on the other hand, is a relatively featureless glow sometimes close to the limit of visibility. It can be distinguished from moonlit clouds by the fact that stars can be seen undiminished through the glow. Diffuse auroras are often composed of patches whose brightness exhibits regular and irregular pulsations. The pulsation period can be typically many seconds, so is not always obvious. Often the black aurorae, narrow regions in diffuse aurora with reduced luminosity. A typical auroral display consists of these forms appearing in the above order throughout the night. Red. At the highest altitudes, excited atomic oxygen emits at 630.0 nanometers. Low concentration of atoms and lower sensitivity of eyes at this wavelength make this color visible only under more intense solar activity. The low amount of oxygen atoms and the gradually diminishing concentration is responsible for the faint appearance of the top parts of the curtains. Scarlet, crimson, and carmine are the most often seen hues of red for the auroras. Green. At lower altitudes, the more frequent collisions suppress the 630.0 nanometers mode, rather the 557.7 nanometers emission dominates. Fairly high concentration of atomic oxygen and higher eye sensitivity in green make green auroras the most common. The excited molecular nitrogen plays a role here, as it can transfer energy by collision to an oxygen atom, which then radiates it away at the green wavelength. The rapid decrease of concentration of atomic oxygen below about 100 kilometers is responsible for the abrupt-looking end of the lower edges of the curtains. Both the 557.7 and 630.0 nanometers wavelengths correspond to forbidden transitions of atomic oxygen, slow mechanism that is responsible for the graduality of flaring and fading. Blue. At yet lower altitudes, atomic oxygen is uncommon, and molecular nitrogen and ionized molecular nitrogen takes over in producing visible light emission, radiating at a large number of wavelengths in both red and blue parts of the spectrum, with 428 nanometers being dominant. Bluey and purple emissions, typically at the lower edges of the curtains, show up at the highest levels of solar activity. The molecular nitrogen transitions are much faster than the atomic oxygen ones. Ultraviolet light from auroras has been observed with the requisite equipment. Ultraviolet auroras have also been seen on Mars, Jupiter and Saturn. Infrared light in wavelengths that are within the optical window is also part of many auroras. Yellow and pink are a mix of red and green or blue. Other shades of red as well as orange may be seen on rare occasions. Yellow-green is moderately common, as red, green, and blue are the primary colors of additive synthesis of colors. In theory, practically any color might be possible, but the ones mentioned in this article comprise a virtually exhaustive list. Other auroral radiation. In addition, the aurora and associated currents produce a strong radio emission around 150 kHz known as auroral kilometric radiation (AKR), discovered in 1972. Ionospheric absorption makes AKR only observable from space. X-ray emissions, originating from the particles associated with auroras, have also been detected. Aurora noise, similar to a hissing or crackling noise, begins approximately 230 feet above the Earth's surface and is caused by charged particles in an inversion layer of the atmosphere formed during a cold night. The charged particles discharge when particles from the Sun hit the inversion layer, creating the noise. Causes of auroras. A full understanding of the physical processes which lead to different types of auroras is still incomplete, but the basic cause involves the interaction of the solar wind with the Earth's magnetosphere. The varying intensity of the solar wind produces effects of different magnitudes, but includes one or more of the following physical scenarios. A quiescent solar wind flowing past the Earth's magnetosphere steadily interacts with it and can both inject solar wind particles directly onto the geomagnetic field lines that are open, as opposed to being closed in the opposite hemisphere, and provide diffusion through the bow shock. It can also cause particles already trapped in the radiation belt to precipitate into the atmosphere. Once particles are lost to the atmosphere from the radiation belts, under quiet conditions new ones replace them only slowly, and the lost cone becomes depleted. In the magnetotail, however, particle trajectories seem constantly to reshuffle, probably when the particles cross the very weak magnetic field near the equator. As a result, the flow of electrons in that region is nearly the same in all directions, and assures a steady supply of leaking electrons. The leakage of electrons does not leave the tail positively charged, because each leaked electron lost to the atmosphere is replaced by a low-energy electron drawn upward from the ionosphere. Such replacement of hot electrons by cold ones is in complete accord with the second law of thermodynamics. The complete process, which also generates an electric ring current around the Earth, is uncertain. Geomagnetic disturbance from an enhanced solar wind causes distortions of the magnetotail. These substorms tend to occur after prolonged spells during which the interplanetary magnetic field has had an appreciable southward component. This leads to a higher rate of interconnection between its field lines and those of Earth. As a result, the solar wind moves magnetic flux from the day side of Earth to the magnetotail, widening the obstacle it presents to the solar wind flow and constricting the tail on the night side. Ultimately, some tail plasma can separate, some blobs are squeezed downstream and are carried away with the solar wind, others are squeezed toward Earth where the motion feeds strong outbursts of auroras, mainly around midnight. A geomagnetic storm resulting from greater interaction adds many more particles to the plasma trapped around Earth, also producing enhancement of the ring current. Occasionally the resulting modification of the Earth's magnetic field can be so strong that it produces auroras visible at middle latitudes, on field lines much closer to the equator than those of the auroral zone. Acceleration of auroral charged particles invariably accompanies a magnetospheric disturbance that causes an aurora. This mechanism, which is believed to predominantly arise from wave-particle interactions, raises the velocity of a particle in the direction of the guiding magnetic field. The pitch angle is thereby decreased, and increases the chance of it being precipitated into the atmosphere. Both electromagnetic and electrostatic waves, produced at the time of greater geomagnetic disturbances, make a significant contribution to the energizing processes that sustain an aurora. Particle acceleration provides a complex intermediate process for transferring energy from the solar wind indirectly into the atmosphere. The details of these phenomena are not fully understood, however it is clear that the prime source of auroral particles is the solar wind feeding the magnetosphere, the reservoir containing the radiation zones, and temporarily magnetically trapped particles confined by the geomagnetic field, coupled with particle acceleration processes. Auroral particles. The immediate cause of the ionization and excitation of atmospheric constituents leading to auroral emissions was discovered in 1960, when a pioneering rocket flight from Fort Churchill in Canada revealed a flux of electrons entering the atmosphere from above. Since then, an extensive collection of measurements has been acquired painstakingly and with steadily improving resolution since the 1960s. 1960s by many research teams using rockets and satellites to traverse the auroral zone. The main findings have been that auroral arcs and other bright forms are due to electrons that have been accelerated during the final few 10,000 kilometers or so of the plunge into the atmosphere. These electrons often, but not always, exhibit a peak in their energy distribution, and are preferentially aligned along the local direction of the magnetic field. Electrons, mainly responsible for diffuse and pulsating auroras, have, in contrast, a smoothly falling energy distribution, and an angular distribution favoring directions perpendicular to the local magnetic field. Pulsations were discovered to originate at or close to the equatorial crossing point of auroral zone magnetic field lines. Protons are also associated with auroras, both discrete and diffuse. Auroras in the atmosphere. Auroras result from emissions of photons in the Earth's upper atmosphere, above 80 kilometers, from ionized nitrogen atoms regaining an electron, and oxygen atoms, so nitrogen-based molecules returning from an excited state to ground state. They are ionized or excited by the collision of particles precipitated into the atmosphere. Both incoming electrons and protons may be involved. Excitation energy is lost within the atmosphere by the emission of a photon, or by collision with another atom or molecule. Oxygen emissions, green or orange-red, depending on the amount of energy absorbed. Nitrogen emissions, bluey-red, blue if the atom regains an electron after it has been ionized, red if returning to ground state from an excited state. Oxygen is unusual in terms of its return to ground state. It can take 3/4 of a second to emit green light and up to 2 minutes to emit red. Collisions with other atoms or molecules absorb the excitation energy and prevent emission, because the highest atmosphere has a higher percentage of oxygen and is sparsely distributed. Such collisions are rare enough to allow time for oxygen to emit red. Collisions become more frequent, progressing down into the atmosphere, so that red emissions do not have time to happen, and eventually even green light emissions are prevented. This is why there is a color differential with altitude. At high altitudes oxygen red dominates, then oxygen green and nitrogen blue red, then finally nitrogen blue red when collisions prevent oxygen from emitting anything. Green is the most common color. Then comes pink, a mixture of light green and red, followed by pure red, then yellow, and finally, pure blue. Auroras and the ionosphere. Bright auroras are generally associated with Birkeland currents which flow down into the ionosphere on one side of the pole and not on the other. In between, some of the current connects directly through the ionospheric layer, the rest detours, leaving again through field lines closer to the equator and closing through the partial ring current carried by magnetically trapped plasma. The ionosphere is an ohmic conductor, so some consider that such currents require a driving voltage, which an as yet unspecified dynamo mechanism can supply. Electric field probes in orbit above the polar cap suggest voltages of the order of 40,000 volts, rising up to more than 200,000 volts during intense magnetic storms. In another interpretation, the currents of the direct result of electron acceleration into the atmosphere by wave-particle interactions. Ionospheric resistance has a complex nature and leads to a secondary Hall current flow. By a strange twist of physics, the magnetic disturbance on the ground due to the main current almost cancels out, so most of the observed effect of auroras is due to a secondary current, the auroral electrojet. An auroral electrojet index is regularly derived from ground data and serves as a general measure of auroral activity. Christian Birkeland deduced that the currents flowed in the east-west directions along the auroral arc, and such currents, flowing from the dayside toward midnight, were later named auroral electrojets.